Welcome all of you. In this session, we are going to start third unit, that is behavior of conductors and dielectrics. This unit, third unit, is behavior of conductors and dielectrics. Okay. So already we know that conductor means it is a material which allows the free flow of electrons. That means it will allow the free flow of current. Then what about dielectric? Dielectric is nothing but it is acting as insulator. Insulator means it will not allow current. Only under some particular conditions only it will allow the current to flow through it. Remaining times it will act as simple insulator only. Okay. So for how these conductors and dielectrics will behave, we are going to study in this third unit. Before that, we need to know what is the importance of current density, continuity equation and all this. So let us go for the introduction. What is the basic definition for current? Current is nothing but rate of flow of charge. Rate of flow of charge. Electric current is nothing but rate of flow of charge at a specified point. At a specified point. From our childhood we are learning the amount of charge that is flowing per unit time at a specified point is called as electric current, or simply rate of flow of charge at a specified point is called as current. That means we can write the current I as simple Q by T, or if you consider only a differential current, then dQ by dt. That is coulombs per second, or current can be expressed in amperes. Okay, so I equal to dQ by dt. That means rate of flow of charge at a specified point is called as current. Now we already know that Ohm's law is a law which relates the applied voltage and current. Ohm's law states that V is directly proportional to I. That means the applied voltage is directly proportional to the current that is flowing to the conductor. If you are applying more voltage, you will get more current. If you are applying less voltage, you will get less current. Right? Like that, V is proportional to I. This is Ohm's law. Okay. So from that we are getting V equal to IR, where R is a constant. But here this Ohm's law is valid only for small simple DC circuits. Small simple DC circuits, we are mostly applying Ohm's law and we are finding the relation between voltage and current with the help of Ohm's law only for small simple DC circuits. But in our electromagnetic field theory, in electromagnetic engineering, we need to study the motion of charges. In electromagnetic field theory, we need to study the motion of charges in liquids, gases, dielectrics. Everywhere we need to study the behavior or motion of the charges. Then this Ohm's law is not enough to study the behavior of charges in those liquids, gases and dielectrics. So here in these advanced studies, that means if we study the motion of charges in liquids, gases or dielectrics, we need to know about a new term called as current density. Current is different, current density is different. So based on this current density, we will derive continuity equation and all those. So in this unit we will study the behavior of conductors and dielectrics based on current density of that material and continuity equation derivations. Okay. So we said that for a complex study of motion of charges in liquids, gases and dielectrics in electromagnetic field theory, we need to know about current density. Then what is this current density? We need to define this current density also. Already we defined the current as rate of flow of charge at a specified point. That means the amount of charge per unit time at a specified point is called as current. I equal to q by t or dq by dt. Then what is current density? We already know that if we apply density for any physical quantity, that quantity divided by area is called as current density. That means current density is the current flowing through unit surface area. Current flowing through unit surface area. That means the current flowing through unit surface area when that surface is held, normal means perpendicular to the direction of current. Okay, so current density is defined as the current flowing through unit surface area when that surface is held normal to the direction of current. That means current by area is called as simple current density, which is denoted as J equal to I by A, amperes per meter square. That means current flowing through unit surface area is called as current density. It is the only magnitude of this J. Current density is denoted as J. Okay. Now, this current density is a vector quantity. It is not a scalar quantity. It is a vector quantity, because here we are defining both the magnitude of current as well as direction of current. It is always perpendicular to the surface that you are considering. So as you are considering both magnitude as well as direction, current density is a vector quantity. Okay. So for vector quantity, generally we will denote with bar. So if you mention only magnitude, then it is enough if you write J. But if you mention it as a vector, then you should represent it with J bar. Okay, J bar is the current density in vector form. Okay, so this is the information about current density. So here in the introduction of this unit 3, first we have seen what is meant by current. The rate of flow of charge at a specified point in a conductor is called as electric current, or the amount of charge flowing per unit time, Q by T, I equal to Q by T, that is called as current. So I equal to Q by T or dQ by dt. Next, generally in small simple DC circuits, we are going to apply Ohm's law to obtain the relation between voltage, current, resistance and all those terms. But if you are going for advanced materials like liquids, gases and dielectrics, and if you want to study the motion of charges in electromagnetic engineering in these materials, then Ohm's law is not enough to study the behavior of charges. We should also know a new term called as current density. So until now you are learning only current. Now you are introducing a new term called as current density. Then if you know this current density, then you can perfectly design a conductor or dielectric, whatever we want. So what is meant by current density? Current density means the current that is flowing through a unit surface area when that surface is held normal to the direction of current. That means if you are holding a surface like this and if your current is flowing perpendicular to the surface, if your current is flowing perpendicular to this surface, then that quantity is called as current density. The current flowing through unit surface area when that surface is held normal to the direction of current. So current density general magnitude is denoted as J, which is equal to current per unit area, that is expressed in amperes per meter square. And as current density is a vector quantity, if you want to express in vector terms, then you should denote it as J bar. Okay, so this is the basic information about current density. These terms are useful in designing these conductors and dielectrics. So here we need to know different types of currents. So first, basic electric current means what we are learning from childhood is electric current is nothing but flow of electrons, that is negatively charged particles. Electric current is generally considered as flow of electrons which are negatively charged particles. Electric current is the flow of electrons which are negatively charged particles. Then what about conventional current? Conventional current means this is our assumption. This is our assumption for solving problems so that it will be easier to express the polarity of the voltage that you are considering. Okay. So conventional current direction is taken as the direction of flow of protons. Conventional current direction is taken as flow of protons, that is positively charged particles. Positively charged particles. Okay. That means generally while solving problems in circuits or any other subject, we will take that if there is a circuit like this, if this is a source, then we are considering the current that is flowing from positive polarity to negative polarity. That means high potential to low potential. This is the direction of conventional current. Conventional current is taken as the direction of protons. Okay, conventional direction is the direction of protons, which says that current is flowing from high potential positive terminal to low potential negative terminal. Okay, when you are taking the direction of electrons, then how will be that actual electric current? Electron direction will be opposite to the direction of protons. That means conventional current direction is opposite to the direction of electric current. That means proton direction is opposite to the direction of electrons. Here we can easily explain. This actual current I or conventional current I is the direction of protons or positively charged particles, and your actual electric current, that means the electron flow will be opposite to the direction of proton current. Okay, so this is the difference between electric current and conventional current. Then you can also define drift current. Drift current means the current which exists in the conductor, due to the drifting of electrons under the influence of applied voltage. Okay, drift current we need to define. That means the current which exists in a conductor due to the drifting of electrons under the influence of the applied voltage. Okay, that means if you apply some voltage in a conductor, then the electrons will move in random directions. They will collide with each other and they will also collide with the adjacent atoms. That process is called as drifting of electrons. And after some time, they will travel in a particular direction with constant velocity called as drift velocity. That later we will discuss about this drift current. There is one derivation also. So the current that is produced due to the drifting of electrons under the influence of the applied voltage is called as drift current. Okay. Next, there is another current called as displacement current. Displacement current. Okay. So what about this displacement current means? In dielectrics, this is particularly observed in dielectrics. In dielectrics, actually there will not be any movement of free electrons. There will not be any free electrons that are available in dielectrics. But if you produce some electric field intensity to the dielectric under the application of electric field intensity under the application of electric field intensity, that means E bar, under the application of electric field intensity, though dielectric acts like insulator, there are no free electrons in dielectrics. That is normal behavior of dielectrics. But under the influence of an externally applied electric field intensity E bar, some charges will start flowing. That means current will start flowing in dielectric coils. That current is called as displacement current or convectional current. So, this displacement current or convectional current is particularly defined for dielectrics. Okay? In dielectrics, actually there are no free electrons available, so there is no flow of current. They will almost act as insulators. But under the application of electric field intensity externally, there will be flow of charges in dielectric coils, which will result in a current called as displacement current or convectional current. Okay? So these are the different types of currents that you will study. Let us revise them once again. Electric current is the general flow of electrons in a conductor which are negatively charged. Conventional current means which we are taking for our convenience to express the polarities of different quantities in a circuit. Conveniently we are taking the direction of current as conventional direction, that is from high potential to low potential. That means positive terminal to negative terminal. This is the conventional direction of current, which is taken as the direction of positively charged particles, that is protons. Next, drift current means that current which results in a conductor due to the drifting of electrons. That drifting process later we are going to study again under the influence of applied voltage. Next, particularly in dielectrics, we are going to see a current called as displacement current. Generally, dielectric will act as insulator. There will not be any free electrons in dielectrics. Under the application of an external electric field intensity, that means if you provide some E, electric field intensity E to that dielectric, then in dielectric also there will be flow of charges. That flow of charges will result in a current called as displacement current or convectional current. Okay, so these are the different types of currents that you can observe in different materials. Like these are observed in conductors. First three are observed in general conductors, and this displacement current is observed in dielectric. So based on this, we are going to design the properties of conductors and dielectrics.